Okay, so here's the final video going over checkup 4d.3, looking at the tram problem, where you have a tram where there is a maximum number of people that can be on the tram and also a maximum weight limit of 6,800 pounds for that tram. And so keeping this thing safe, they would have to keep it within both of those constraints to have the proper load of people on that tram. So the first equation or inequality that we get is the fact that it can carry a maximum of 60 passengers. So that's where the x plus y is less than or equal to 60 comes from. So if we're using adults for x and children for y, those two numbers have to add up to a number that is less than or equal to 60. And the other inequality pertains to the weight limit. And so that is the adult is 180 pounds, a child is 80 pounds, and a maximum total weight of 6,800 pounds. That's where the second inequality comes from. I've already graphed them. Just a quick review of how we graph those. We're graphing them just like lines. We're going to talk about the shading because it is an inequality in a minute. And so with the first one, the x-intercept, x is 0, y would be 60. That just means if there are no adults, you could have 60 children on there. So the x-intercept would be 60, 0. And the y-intercept for that one, if it was all adults and no children, oh, sorry, actually adults is x, children is y. If it was no adults and all children, oh dear, you would have 0 adults, 60 children on there. So that's where I got the 2 points where that line crosses the x and y intercepts. That's where I got the blue line. Notice both intercepts are at x is 60 and y is 60. For the green line, the one pertaining to the weight, if x is 0, so if there are no adults, you could have 85 children, or sorry, yeah, 85 children would give you a total weight of 6,800 pounds. So this is just substitute and solve. So our x-intercept, if you put y is 0 into that equation, divide both sides by 80, you could have 85 children and hold on, I think I'm getting this backwards. So if y was 0, our x-intercept is when y is 0. So if y is 0, there's no children, it's all adults, 180 pounds each. 6,800 divided by 180 is 37.8. So you could have 37.8 or 37 if we were to round down, it's a maximum limit. 37.8 adults and 0 children um, would take that thing to its weight limit. And if it was all children, no adults, you could have 0 adults, 85 children. So that's where I got the x and y intercepts for the green line and then connected the dots. So the next part is because these are inequalities, we're not just looking for the intersection point on that one. We'll talk about that at the end. That's actually that question C at the very end has to do with the tram being filled to capacity in terms of number of people and weight limit. So we'll talk about that intersection point. But when we're talking about the inequality, we're interested in the regions that we get. So we could use for both of these that test point at 0, 0. So if you put 0, 0 into the first equation, x is 0 and y is 0, you get 0 is less than or equal to 60, which is true, which means 0, 0, and all of the other points underneath that line make that inequality true. For the other inequality, we could do that same test, so put 0, 0 in for the weight inequality. 180 times 0 and 80 times 0, both of those are 0. Of course, you have 0 people, you have 0 pounds of weight in there. 0 is less than or equal to 6,800. That is true. So that means the region underneath the green line makes that inequality true. So everywhere down here makes it true. So what we end up with are 4 regions in our graph. And the region that is double shaded is the region that makes both inequalities true. That's the region that we're looking for. So that is the region with the double shading. So it's underneath the line. So what would be a good color to indicate that? How about yellow? So this region right down here, that is the region that is shaded underneath both inequalities, the yellow region. So you could pick any point within that region, any XY coordinate point. And what a lot of people actually on this one made a mistake on, it wasn't the graphing or which side was shaded. That was pretty darn good. But what people just made a mistake on was just kind of slacking off on this part, what each region means in terms of the scenario. So I had quite a few people who said, this region, the one that I've got shaded yellow, makes both inequalities true, and then the other three regions make one or the other inequality true. Really, really brief description. Don't forget, the in terms of the scenario part means you're talking about the people limit and the weight limit. So if you are in the region that's shaded yellow, that means that the number of adults and children is within both the number of passengers and weight limits. So those combinations are going to be less than or equal to 60 people, and it's going to be less than or equal to 6,800 pounds. So the other three regions, let's go with the blue one. Remember, that's the region that is underneath the blue line, but not underneath the green line. That small region. So that's the region that only makes the blue inequality true, the one pertaining to the number of people on the tram, but not the weight line. Because if you look at that region, it's above the green line, under the blue line. So that means that it's within 60 people, but it's above 6,800 pounds. So the number of people, oh, I just realized, typo up here, should be the number of people is within both the number of passengers and the weight limit. So this one, the number of people is less than or equal to 60, but the weight is greater than 6,800 pounds. So too heavy. This region over here, which is within, so it's underneath the green line, but it's above the blue line. That means it's within the weight limit, but it's too many people. So you can pick any point within that region. So it's too many people, but within the weight limit. And finally, there is another region out here, our fourth region. That's above both lines. That means it's too many people and it's too much weight. So again, discussing that in terms of the scenario is too many people, too much weight. Okay, and that's going to be the case for any system of two linear inequalities, is assuming that they intersect somewhere, they're not parallel to each other, then they are going to have four regions created, and one region makes both inequalities true, one region makes one but not the other, one region makes the other but not the first one, and one region makes neither inequality true. You always get those four regions, just a matter of interpreting which region means what. So the final question is, what combination of adults and children would fill the tram to its capacity? So that means you have exactly 60 people and it's exactly 6,800 pounds. That sounds to me like a system of equations instead, which is what we were talking about during the first part of this unit. And so you're looking for the intersection point. And so, of course, you could use Desmos, put both of those equations in Desmos, and it would give you the intersection point. On this equation, you could also use linear combination because they're both in standard form. You'd have to multiply the top equation or divide the bottom equation by something so that a term would cancel out, and you could solve that, just like we did previously in this checkup. You could also solve the top inequality in terms of x or y, and you could use substitution. Whatever strategy you use, what you're trying to do is solve a system of equations rather than a system of inequalities. So instead of inequality signs, we have equal signs. And if you solve that, you get 20 adults, 40 children. So that would weigh 6,800 pounds and be exactly 60 people. Notice 20 plus 40 is equal to 60.